Hi everyone, welcome back. So when we were talking about difference equations and we're trying to figure out the local stability of difference equations, one of the things we did is we tried to use something called jury conditions to determine if the eigenvalues of the matrix all had modulus less than 1. In the last video, we showed that there was something analogous for differential equations, where if all the roots of the characteristic polynomial have negative real part, then all the solutions limit to 0, which is the equivalent to stability for these particular examples. Now, the question is, of course, are there any quicker ways of figuring out whether or not all the eigenvalues of all the roots of the characteristic polynomial have negative real part? And the answer to this is yes. And we'll, in today's lecture, as well as in Thursday's lecture, we'll be going through a couple different conditions, some of them necessary and sufficient. That's the one we're going to be talking on in this video, the Routh-Hurwitz criteria, and some that are just necessary and some that are just sufficient for determining if the eigenvalues have negative real part. So let's go ahead, and the first thing we need to do is we need to define something called a Hurwitz matrix. Hurwitz matrix. And there are a couple of different ways of defining this. I'm going to give a definition specific for the case of characteristic polynomials of differential equations. There is a slightly more general definition as well, but this will be sufficient for our purposes. So given the polynomial p of lambda is equal to lambda to the n plus a1 lambda to the n minus 1 plus a2 lambda to the n minus 2, summed up all the way to a n minus 1 lambda plus a n, where each of our ai's are real numbers. The nth Hurwitz matrix, Hurwitz matrix of the polynomial is Hn is going to be equal to, and I'm going to write this out in a sort of weird way. Actually, let me go ahead and say, let's go ahead and say a couple things. I'm going to say that a naught is equal to 1, and ai is equal to 0 for I less than 0, and also ai is equal to 0 for I greater than n. So note that we only have coefficients for a1 through an that are non-zero, except for a naught, which would go here. So that would be a naught. But we're just going to say that's equal to 0, equal to 1. Then we're going to define our matrix by, oh, sorry, that's not a bracket, that's a matrix. Starting with a1 in the upper left, and then in the first row we're going to go down by 1 as we go to the right. So this is going to be a naught, and then a minus 1, a minus 2, and so on. And of course, the a minus 1 and a sub minus 2, those are going to be 0, and a naught is going to be 1. So all the way over to, it's going to be, it's going to end at a minus n plus 2, since this is going to be an n by n matrix. So that's what happens as we go along the row. What happens as we go down the column? Well, then for each step we add by 2. So this is going to be a3, and then we're going to go to a5, etc., all the way down to a 2n minus 1. 2n minus 1. And this is going to be, and of course as we go along the row, we're going to go down by 1. So a2, a1, a naught, and then it would be a minus 1. And so on all the way to a minus n plus 2, and so on. And so this would be a4, a3, a2, all the way to a minus n, minus n plus 4. That one was minus n plus 4, and this one is minus n plus 6. Plus 6, and so on. So this over here would be a 2n minus 2. That minus 1 should be in the subscript. Sorry, minus 1, a 2n minus 2, and so on until you get to a n. Okay, so this is a sort of weird matrix, but what we're doing is as we go to the right along a row, we're subtracting the index by 1. As we go down down from column to there, as we go down within the column, we add by 2 each time. And of course, if your coefficient isn't in your polynomial, then it's equal to 0, unless it's a not, in which case it's equal to 1 because we have an implicit 1 in front of the lambda to the n. Okay, so that's the nth Hurwitz polynomial, and the n Hurwitz matrices for k less than n are given by the principal minors of h sub n. That is to say, we have h1 is going to be just equal to the first principal minor up here. So that's going to be just the matrix, that's the 1 by 1 matrix. And we have h2, which is going to be equal to the 2 by 2 matrix. So that's a1, a0, a3, a2. h3 is going to be equal to the 3 by 3 matrix. So that's going to be a1, a0. Actually, since this has a not there, we can go ahead and replace this by a1, 1, a3, a2. And we have h3, which is going to be the third principal minor. That's going to be a1, a0, a minus 1, a3, a2, a1, a5, a4, a3, which is going to be equal to a1. Oh, sorry, you can't see this. A1, 1, 0. And a3, a2, a1, a5, a4, a3, and so on. Okay? And of course, the Hn matrix itself, you could rewrite in a slightly different way by replacing all the coefficients that are 0. Though it's a little bit hard to see what's going on here, so this is why I didn't do this way originally. A1, 1, 0. There are a bunch of zeros. And then you have a3, a2, a1, 1, 0, and a bunch of zeros, and so on. And of course, down here you end up with zeros, since that's a2 and minus 1, that's clearly bigger than n. But you end up with an an here. So it's a really weird sort of matrix, but now we've defined it. So now, what can you do with this super weird matrix? Well, what you can do is, it turns out there is a very nice theorem. This is called the Routh-Hurwitz criteria, so the main topic of today's lecture. We're not going to prove this theorem, but it is useful to know. Criteria, which is that all the roots of the polynomial p of lambda is equal to lambda to the n plus a1 lambda to the n minus 1, and so on, all the way to a n minus 1 lambda plus a n, have negative real parts. So this is the stability criteria that we want to give. Have negative real parts if and only if the determinant of hj is greater than 0, so it's strictly positive, for j in 1 through n. Okay, and the proof is beyond the scope of this class. Beyond scope of this class. We will give a verification for n equal to 2, just to give you a flavor of it, but it gets pretty complicated. So beyond scope, of course. But, so, let's go ahead and give a proof for n equal to 2. So, proof for n equal to 2. Okay, so what do we have? We have p of lambda is equal to lambda squared plus a1 lambda plus a2 is equal to 0. Well, we know that lambda 1 is equal to minus so is equal to minus a1 plus or minus, but let's have this lambda 1 be the plus version, plus the square root of a1 squared minus 4a2 over 2. And we'll have lambda 2 be equal to minus a1 minus the square root of a1 squared minus 4a2 over 2. And what are the Routh-Hurwitz criteria? So we only need h1 and h2. So Routh-Hurwitz criteria says is determinant of h1, which is equal, determinant of h1, which is equal to determinant of a11, oh sorry, not a11, just a1, has to be greater than 0. So that of course implies that a1 has to be greater than 0, and determinant of h2, which is equal to the determinant of, well, h2 is going to be a1, 1, a3, a2, a1, 1, a3, a2, but of course a3 here is 0, so this is equal to the determinant of a1, 1, 0, a2, which is equal to a1, a2 is greater than 0, and together, well, this implies that a2 is greater than 0. So the case of n equals 2 is rather simple because we only need these two to check these two things. a1 and a2 both need to be greater than 0. And that is both necessary and sufficient according to the Routh-Hurwitz theorem. So let's try to prove this now. So now there are a couple different cases. So let's start with the forward case. Well, the forward case is for, we're going to start by saying that the Routh-Hurwitz criteria are satisfied. So a1 is greater than 0 and a2 is greater than 0. And we need to prove this for both the complex and real cases. So let's start with assuming that they're both complex. So suppose lambda 1 and lambda 2 are both complex numbers, and they are, since the coefficients are real, if they're complex, if they actually have a non-trivial imaginary part, then they're complex conjugates. So that is to say that the stuff inside of the square root is negative, and so you end up with an imaginary number layer. Well, when you do this, the real part of lambda 1 is equal to the real part of lambda 2. And what is that? So that's just equal to this part, right? So the real part is equal to minus a1 over 2, which of course is less than 0. Because a1 is positive, and so minus a1 over 2 is negative. Okay, so that shows that in the forward case we have a1. In the imaginary case we know that a1 is less than 0. That both of the real parts. We know that a1 is minus a1 over 2 is less than 0. So both of the real parts of the both of the eigenvalues are less than 0. So that proves it for the imaginary case. The real case is a little bit more complicated. So suppose that lambda 1 and lambda 2 are both real. Well, then what we have is we know the stuff underneath the square root sign must be greater than or equal to 0. So minus a1 squared minus 4a2 has to be greater than or equal to 0, because otherwise it would be complex instead. So clearly, we know that lambda 2, oh, what just happened? Come back. Oh, somehow that drew a line. Okay. So clearly, lambda 2 is less than 0, since both minus a1 is less than 0, and minus the square root of a1 squared minus 4a2 is also less than or equal to 0, because otherwise it would be imaginary instead. So we just need to show that lambda 1 is less than 0. So also, we know that a1 squared minus 4a2 is less than a1 squared, because you're subtracting by, because we know that a2 is greater than 0, so you're subtracting by a positive number. So if you subtract by a positive number, you're clearly going to be less than what you started with, since a2 is greater than 0. Now, of course, this implies that if you take these are both positive numbers, and so you subtract, you can take the square root of both sides, so you get the square root of a1 squared minus 4a2 is less than just a1, which implies that minus a1 plus the square root of a1 squared minus 4a2 is less than 0. But of course, that's just the that's just the numerator of lambda 1, which implies that lambda 1 is less than 0. Okay, so whether or not lambda 1 and lambda 2 are complex or real, you know that the real part of them is negative, assuming that a1 and a2 are both positive. So let's consider the backward case. So we're going to let the real part of lambda 1 be less than 0, and the real part of lambda 2 is also less than 0. And the proof is pretty straightforward. You just go backwards on all of them. So first we'll consider the case where they're complex. Suppose lambda 1 and lambda 2 are complex, and they're complex conjugates. Well, then we have that the real part of lambda 1 is equal to the real part of lambda 2, again, which is equal to minus a1 over 2. And since both of these real parts are negative, we know that that implies that a1 is positive. Okay, well, that shows what for a1, and now we need to consider also a2, since we need to show that both a1 and a2 are positive. So also we have that a1 squared minus 4a2. Well, the stuff underneath the square root has to obviously be negative, or you wouldn't be imaginary, or you wouldn't have an imaginary, non-trivial imaginary part. So this implies that 4a2 is less than a1 squared, is greater than a1 squared, which of course is greater than 0, which implies that a2 is also positive. Okay, so again, the complex case is the easiest. But now let's suppose that they're real numbers instead. Well, if they're real numbers, then we can just say that they're both less than 0, for their real parts to be less than 0. The real part of a real number is just itself. And we know that a1 squared minus 4a2 is greater than or equal to 0, or they wouldn't be real. So now we can take a look at each of the lambdas separately. So let's say that lambda 1 is equal to minus a1 plus the square root of a1 squared minus 4a2 over 2. But of course we know that the stuff underneath the square root is positive, and so that means that this half is positive, but the entire thing is less than 0. Well, in order for the entire thing to be less than 0, if one half of it is positive, the other half has to clearly be negative. So that implies that minus a1 over 2 is negative, which implies that a1 is positive. Okay, and we also have that, what else do we know? We also know that this thing also implies that minus a1 plus the square root of a1 squared minus 4a2 is less than 0, right? That's just multiplying both sides by 2. But now we can rearrange this. So we end up getting the square root of a1 squared minus 4a2 is less than a1. And we square both sides. Since these are both positive numbers, squaring it doesn't change the direction of the inequality. So if we square both sides, you get a1 squared minus 4a2 is less than a1 squared. Subtract out a1 squared from both sides, you end up with minus 4a2 is less than 0, which implies, of course, that a2 is also greater than 0, and this proves the theorem. So this proves the theorem for n equal to 2. So now you'll notice that this is pretty complicated and we did a lot of case-by-case analyses. For the higher cases, for n greater than 2, it's also pretty complicated. Though in the book they do write out some of the easier versions of some of the higher cases. So let's go ahead and let's call this an example, though I don't know if this is exactly an example. So for n equal to 2, we have a1 is greater than 0 and a2 is greater than 0 for the Hurwitz criteria. For n equal to 3, well, the condition after you take the determinants actually ends up becoming a1 is greater than 0, you need a3 to be greater than 0, and you need a1, a2 to be greater than a3. For n equal to 4, you end up with a1 is greater than 0, a3 is greater than 0, a4 is greater than 0, and a1, a2, a3 is greater than a3 squared plus a1 squared, a4. Yeah, that looks like what I have in my notes. n equal to 5, it becomes super complicated. Let's see. Let me go ahead and write this out just for completion. So we have ai is greater than 0 for I in 1, 2, 3, 4, 5. And we have a1, a2, a3 is, just a moment, let me double check this. Sorry, I was saying a1, a2, a3, that has to be greater than a3 squared plus a1 squared, a4. So that was the same condition we had for the case of n equal to 3. And we also have another even more complicated condition, a1, a4 minus a5 times the entire quantity times a1, a2, a3 minus a3 squared minus a1 squared, a4 is greater than a5 times the quantity a1, a2 minus a3, that entire quantity squared, plus a1, a5 squared. Okay, so as you can see, this gets really complicated super quickly, and proving it is even more work. So we're not going to deal with that, but you should just be aware that these criteria do exist. So just like the jury conditions were a little bit finicky to apply for a higher n, the same is true for the Routh-Hurwitz conditions criteria. But they are useful to know because they do give you a easier check than actually computing all these determinants, or actually computing all the eigenvalues or roots of a polynomial. Let's go ahead and give an easy corollary, though. So this is going to be corollary 4.1, which is just a necessary condition, but not a sufficient condition. So given our polynomial as standard is equal to lambda to the n plus a1 lambda to the n minus 1 plus dot 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 plus a1 n minus 1 lambda plus a n, where ai is in the reals. If all of the roots of p of lambda have negative real parts, so by which we mean they're either complex with negative real parts or they're just real and are negative, then ai is greater than 0 for all I1, 2 through n. So basically, you need to have positive coefficients on all of them if you want to satisfy the Routh-Hurwitz criteria. And you can see this by looking at this is a corollary of the previous theorem, of theorem 4.4. But we can also give a direct proof, which will be a little bit more informative. Let's go ahead and give a direct proof of this theorem. So we're going to start by just listing out all the roots. So let minus r1 minus r2 minus rk be the real roots of p of lambda, counting multiplicity. So if you have a double root, you include it in this list twice. And we're going to let minus c1 plus or minus id1 through minus ck2, sorry, let's make that k1, this is k2, plus or minus idk2 be the complex roots, counting multiplicity. Okay, so we're just listing out all of them, and we have Ci, Di, R, and Ri are all real numbers, of course. And note that we have that Ri, sorry, actually let me not use I, because I is being used for the complex coefficient. Let's use J here. Cj, Dj, and Rj. So note that Rj and Cj are both greater than 0 by assumption. Because that was their assumption that they had negative real parts. And of course, we put a minus sign in here. So Rj and Cj are positive by assumption, strictly positive. Well, then we know that then we can factor out our polynomial. So this is one of the facts about the roots of a polynomial. You can factor by them. So then this is equal to lambda plus R1, the product of all these, all the way through lambda plus RK1, and lambda plus C1 minus ID1 times lambda plus C1 plus ID1. And of course, you have the product of all these complex terms. And it's going to be lambda plus ck2 minus idk2 times lambda plus ck2 plus idk2. Okay, so we're just factoring out our equation, and let's multiply together the complex terms. So then we have, again, we're just copying down the real terms, and you end up with lambda squared plus 2c1 lambda plus c1 squared plus d1 squared times all the way through lambda squared plus 2ck2 squared, sorry, not squared, ck2 lambda plus ck2 squared plus dk2 squared. Note that all coefficients in the factored equation, are strictly positive, so they're greater than 0. So after multiplying out, all the coefficients of the multiplied out equation, a1 through an, are also greater than 0. Okay, so this is a direct proof, and this will come in handy at various points because it's a quick check. If this is not the case, then you know that it doesn't have not all the roots have negative real parts. And if not all the roots have negative real parts, then you know that the differential equation doesn't have all solutions tending towards 0. And in a moment, we'll discuss how, sorry, not in the moment. In the next set of lectures for Thursday, we'll talk about how this means that they aren't stable in the same sort of sense as we talked about local stability for difference equations. Okay, however, in the next video, we'll give some more examples of this, and some of this was a little bit theory heavy. So I will see you in the next video. Actually, this is 4.5a, because we're about to go to 4.5b. Okay, I will see you in 4.5b.